Okay, so thank you. Okay, good afternoon. As I wrote in this piece of paper, I mean, these notes are not followed strictly during this lecture, the notes I gave. The idea is that the notes I gave you is a kind of dictionary for you, for people who do not know some basic notions of differential geometry. But during this lecture, I just want to stress motivation and give you intuitive ideas. So let's start from general considerations. Let's start from the title of the school. So it's topological aspects. It's two words, and then there is quantum, and so on. So basically, topological aspects means that we will be involved in topology. But the point is that many topological invariants are written in terms of differential form. So topology somehow is linked very naturally to differential geometry. On the other hand, another typical connection of topology is typically connected to symmetry. And the concept, the mathematical implementation of symmetry is group theory. So the group is another object that is linked to topology, and a kind of fusion of these two is the theory of bundles. So the plan of this lecture, and if you go to the quantum side is typically operators from the point of view of mathematics. So the functional analysis. So, and also, for example, in the path integral. And now the point is really aim of the school is to create a link precisely between these two branch of mathematics in physics. So then you get somehow topology in quantum physics. So the plan of this lecture is that in the first lecture, I will go a little through differential geometry, the second lecture to group theory, and the third lecture to bundles. Let's start with differential geometry.
Excuse me?
Yes, please.
Would you be so kind and not change the paper so quick if one likes to copy, if that's possible?
Okay. I don't know what is the typical thing of the school, maybe because... Oh.
Maybe you can either maybe provide the notes after the lecture, Pieralberto.
Okay.
If you can scan them, if that's possible.
Yes.
Would that be a solution?
Yes, I can do that.
Would that be okay also for the students, or you rather just that Pieralberto takes a bit more time when changing the sheets of paper? Well, someone needs to speak up.
Providing the notes is quite useful.
Okay.
Thank you.
Perfect.
So I'm not a very nice writing, but anyway. So let's start with differential geometry. And the first question is, you already have topology, and you have a topological space, and now the natural question is how to introduce a differentiable structures in a topological space. So we know that topological space, it has provided your space with a set of open sets and so on. So differentiable structure means that they want to introduce basically derivatives and variation of this concept. That's the simplest one, just f prime of x is equal to the limit, let's say at h goes to 0. And so the concept of limit is already in topology, so I don't need to add anything. But then I have f of x plus h minus f of x divided by h. So I need to have the structure which permits me to introduce the plus. So basically it's a vector structure in the domain. And also from the following expression, I also need a vector structure in the codomain. So a topological space, which of course has all these structure, is Rm. So the real space in m dimensions, so m being some natural number, it has both vector and differentiable structure. And for example, if I have a surface which is embedded in an M, one can introduce on it from Rn the induced differentiable structure. So if I am, let's say, some surface, for example, I can embed into R, in this case R3, and I can use the differentiable structure over T. However, in many cases, we would like to have an intrinsic structure. So an intrinsic differentiable structure without embedding. Let me just to think two examples. Our universe is not embedded in nothing. Another example may be, for example, when you think in terms of Brillouin zone, a Brillouin zone in some metal or in some insulator which has some dimensionality, not obvious to think it in terms of embedding in a higher dimensional space. So the universe or the Brillouin zone are typically cases in which you would like to have an intrinsic differentiable structure, and the intrinsic differentiable structure in a topological phase is accomplished by the notion of manifold. So, okay. What is a manifold? Well, a manifold is a topological space such that each point let me call the manifold M. I usually use a letter M for the manifold. So each point P, which belongs to M, has an open neighbor and in order to introduce an open neighbor, you just need topology. So just need the topology. Homeomorphic. So it means you have a continuous map into an open set and invertible map to an open set of some Rm. Rm. Written in formula, for every P belonging to M, there exists an open neighborhood of P and an invertible continuous map. Let's call phi P because it's a neighbor of P from UP to Rm, which is called a chart. And M is called the dimension. So you are now of the manifold. So you see now you can introduce the concept of dimension, which is not so clear in a topological space. Now you have introduction of a dimension. And let me just draw some, it is not the end of the story, but let's imagine you have your typical, a surface like this. So you have 2 points, let's say P1 and P2, and you have two neighbor of P1 and P2. So you have some neighbor of P1, and so that is U of P1. Now you have a neighbor of P2, so you have a neighbor of, sorry, I just got it outside, but U of P2, I should be like this. And you have a map. You have a map phi of phi 1, which go, for example, in this case into R2, and you map your neighbor there with some neighbor that you can use some coordinate X in R2, for example. Then you have a neighbor in of P2, so you have a map phi of P2, and again you have you can map into R2. You have another open set in R2. Then you have C. You see here you have an intersection of these two. And correspondingly, you will have some intersection here, which region which correspond to this intersection. And now the crucial point is that I can construct a map, which is phi of P2 to the so phi of P2 is a map from phi of P2 to the -1. So it goes from R2, composed phi of P1. And now is you go from here by the inverse map, you go to the manifold. But now in this point, which are here, you also have a phi of P2, the domain is in domain of phi of P1. And so you can get a map from here to here, which is just a map from Rm to Rm. So this map is called a transition function and is defined clearly on the image of the intersection, as I showed. But the crucial point is that in Rm, there exists a differentiable structure. So we can require the differentiability, for example, of some degree. Let's say R, so for CR, which R can be 0, 1, infinity, it depends, for exactly this map, for phi of P2 composed, phi of P1 in mind this composed with phi of P2 to the -1 of X, for X belonging to, now you have to be careful, it's phi of P2 of U of P1 intersection P2, which goes into some point which will be in phi of P1 of U1 P1 intersection the neighbor P2. And so now this object is a map from, this map is from Rm to Rm, so okay, you can perfectly define what you mean by to have a differentiability of order R. And you can cover your space if you have a set of U of Pi, so which a set of open sets, which runs in some index set I.
Excuse me, could I still see the last page one?
Sorry?
Could I have a moment to copy?
Is it still okay? I just move.
I need the last line. Thank you.
Before I was, it seems to have the full.
Okay, thanks.
Okay. So now, if suppose you have why now it's not all the piece of paper away. Suppose you have a set of these open neighborhood which cover completely in your manifold, your topological space. So if there is a set of the European set such that the union of all these open sets is just equal to M, well, this is called an atlas, so of M, just like the atlas of a geographic context. So let me just give you an example and counter example. An example is, let's say, S1, very simple example. So you have your S1, and now you cover it by two open sets. In one, you exclude, for example, you can put some angle phi. Now in one, you exclude the point 0. So your one open set will be this one. So this is U1. Another one, you exclude pi. So you exclude pi, and so the open set now will be this one. So I have, and this is U2. So if you have, for the one you have excluded the 0, this is phi 1, let's say, phi 1 is from a point which is in U1, you go to some set which is in R, which is, you exclude the 0, so you go from 0 to pi. This is an open set in R. Instead, phi 2, this point which are in U2, you go instead, you have excluded pi, so from minus pi to pi. And now it is clear that if you make the transition, so phi 2 to the minus 1 compose phi 1, what you do is okay, if you have some point which are in the intersection of U2 and U1, so for example here from 0 to pi, you can just map phi into itself if phi belongs to the interval 0 pi. Whereas if instead you have phi which goes, so you phi to the minus 1, so it is from minus pi to pi, okay? So you want to go to from 0 to pi. So you have to add, you have the region which is here, which you have not, is not included here, and you have to add a 2 pi. So phi goes into phi plus 2 pi if phi belongs to the interval minus pi 0. So that you recover also the other. So it means that you have found a covering of your SU1 and you have mapped into two region open sets, which is minus pi for one case, and the other is 0 up to 2 pi in the other case. So they have one dimension, dimension 1. This map is clearly continuous and invertible in the correct domain. So in U1 cross intersection U2, so you have proven that S1 is a one-dimensional manifold. You can also do, of course, the same with S2, if you consider S2. Again, you can use, for example, some upper region of your sphere and the lower region of your sphere. And now the only thing which changes is basically the phi goes around all this, the angle around this region. But so if you define theta instead the angle with respect to the vertical, so you have that, so this was U1. The phi goes in both cases from 0 to pi. And the theta, for example, goes, in one case, it goes from 0 to pi half, let's say, plus some epsilon positive. And in the other case, so this is, let's say, phi 1. And phi 2 goes from, for theta, which goes from pi half minus epsilon to pi. So these are open sets, and then this is a two-dimensional manifold. So now a counter example, just to have an idea, counter example. Suppose you consider the following subset of R2. So X1 is equal to, in absolute value, to the absolute value of X2. If it is a manifold, I can take, for example, this piece here, this open interval is one-dimensional. I can certainly map this into one-dimensional subset of R1. However, if I eliminate one point, the 0, 0, if I remove 0, 0 from, let's say, this object here, this topological space, then we see that it split in 4 disconnected components. But you immediately realize that if you have a one-dimensional object which is homeomorphic to R, if you remove one point, necessarily this is split in two connected components. So there is no way in which you can remove one point from R and you get four disconnected components. So this is not a manifold. You can generalize the idea of manifold if instead of to a manifold with boundary, a manifold with boundary is in the case in which you make the same procedure, but you require that the space is locally homeomorphic, not anymore to some Rm, but to some Rm plus. It means that the one coordinate, for example, x1, is only considered to be positive of 0. This construction provides a manifold with boundary. For example, let's consider one object like this. This is our manifold with boundary. And now we can cover it, for example, the boundary is, consider, for example, this object here. So this is, the idea was that this was a kind of object like this. Then, of course, you can construct an open neighbor here, let's see, U of t. This will be mapped into, again, R2. But now, because this boundary, this is not an open set in R2, but is because the open set, let's remember that the open set in Rm plus are given by open set of Rm intersection with our Rm plus. So it means that you have included this piece here, which, however, cannot be for an open set of Rm, or 2 in this case. So this is a manifold with boundary, and the boundary of M, by definition, is the union of all the P such the inverse image when you take y of u of t intersection the boundary of Rm plus, and you cover all of this with so many of these u of p. So now you have idea of what is a manifold and what is a manifold with boundary. And now let's try to have some maps between manifolds. So you have a map. So you have M and N are manifolds. And that's F is a function which goes from M to N. And which is, let's say, continuous. Which means that the inverse image of an open set in N is an open set in M. So to define this, you only need a topology. Now you want to introduce for this function a differentiable structure. How you can introduce a differentiable structure? in this case? Well, the trick is that you have a map from M to N. But now locally in M, you have a map from an open, okay, maybe it's from, this is here is an open neighbor of some point in M. And you have a map phi of P to some Rm. And similarly, you have, let's say that f of P is equal to Q. And now you have, because this is a manifold, you also have a map phi of Q into some Rn, which is, so M is a, so M is a dimension of big M, and N is a dimension of big N. So now again, you have to see the trick. Now this object is perfectly well defined in terms of differentiable structure. So if I go from here, I go from Rm to the neighborhood here, through F, down to the Rn. So it means that I do Cp to the -1, compose F, compose phi Q. Well, this I can certainly require to be a differentiable function because it is a map between Rm to Rn. And so here I also have some coordinate. Let's say a coordinate. So x1 up to xn. And here I also have coordinates. So y1 up to yn. And so what means the degree of differentiability in terms of this is that every yi as a function of x1 up to xm for I equal from 1 up to n, right, is of class CR, with the R that you want. Well, you have introduced a differentiable structure of class CR inside of your map F. So you say that, so F, so F is of differentiable structure class CR if for every P in the domain of a chart phi of P with Q equal to F of P, which belongs now to N, in chart, we have that this map F equal to phi Q, composed F, composed phi P. The -1 is of class CR. So now you have in this way, you have introduced a differentiable structure for functions, maps between manifolds. So originally the manifold, there are topological spaces, so there is no way in which you can, from the topological point of view, introduce a differentiable structure, but through the chart, you can do it locally, and then this is sufficient to define what you mean by a differentiable structure of some class CR, which may be 1 or infinity, or typically when you call smooth, if you say that the F is smooth, it means typically CR is C infinity. Okay. If you have a map between two manifolds which is invertible, well, this is called a diffeomorphism of class C smooth, a smooth map invertible between two manifolds so must be invertible and smooth, is called a diffeomorphism. Okay, so this is the idea to introduce, first of all, differentiable structure inside the topological space. Now, another typical feature that you have in RD is that you can introduce a tangent vector. Suppose you have a surface in RD and you have a curve along the surface. Well, you pick a point, and you define the vector by taking the tangent to the curve. And now what we do for a manifold, well, naive idea would be, okay, I take some point in my manifold, I have some map, I have some neighbor of this point, I have some chart, phi. I have defined this object as a vector tangent to a curve. So I have a curve gamma, which is a map from an interval to our manifold M, which sends points which are in the interval, let's say 0, 1, to points which are in M, which I denote by gamma of T. And so this is our curve. This is our curve. And naively you say, well, I have my chart phi, and why not define phi composed gamma? So gamma takes me from I, from 0 to 1, to M, and so that is gamma, and then phi maps it into some Rm. So certainly this is a differentiable, this is differentiable. You can differentiate, and so you can define a tangent vector, but this doesn't work. This doesn't work because if I change chart, so I take one chart, and I take a second chart, in which still I have the same curve, the piece of the curve that I am interested in to take my tangent vector, this will be mapped into some phi2 composed gamma, and phi1 composed gamma will be some curve here, which is, let's say, in R2, and correspondingly we have some tangent vector. Phi2 again is some you map into another curve, but now the tangent vector could be completely different from this. So the point is that there is no reason for constructing charts that the vectors associated to phi1 composed gamma may perfectly be different from those associated to phi2 composed the same curve gamma. So what is the idea? Well, the idea is that you use a smooth, at least it's C1 or C infinity, doesn't matter, real function in M. So it's the function now is a map from M to R. And now you define F composed gamma. So according to this rule, you have a map from I, so the gamma to M, and then from M to R, which is F. Again, this is perfectly differentiable.
What do you denote by I again?
Sorry?
What do you denote by I again?
I is the interval 0 to 1. Okay? It's fine?
Yes, thanks.
So this is a map which you send your. So this is perfectly differentiable. So I can take the derivative, f composed gamma of t, evaluated at t equal to 0. Well, this is perfectly well defined. And now what is the trick to make contact with our original intuition that, okay, we take our curve in the manifold, we map into the charge? Well, just use charge in intermediate step. So now use charge in the intermediate step. What do you mean by this? Well, you just do the following. You have originally your f composed gamma, and certainly you can write as f composed, let's say, phi p to the minus 1 composed phi p composed gamma. So this was our original idea. And now you have added this piece here. Now, this is perfectly differentiable because this, let's remember that phi composed phi p to the minus 1 is a map which sends Rm to R. But also phi p, as we have seen from gamma, is a map from I to Rm. So it's also differentiable, both differentiable. So here you map t into some coordinate x, then you send x to f of x. And so when you take the derivative of f composed phi p to the minus 1 composed phi p composed gamma, evaluated at t equal to 0, is what? It's a sum from, let's say, mu from 1 to n. And now this is a map from x to f of x. So p over dx mu of f composed phi p to the minus 1 of x. And now you have the other derivative, the composed derivative. So derivative with respect to t of phi p composed gamma, evaluated at t equal to 0. But this object here is what we call is a coordinate, so it's some x mu of t. So in the end, what you have found is that this is really sum of a mu from 1 to n of the derivative of x mu of, let's say, of f times the derivative of dx mu over dt, evaluated at t equal to 0. And so this was our original intuition. But now what you see that our original intuition doesn't work, but it works if we is combined with this derivative. So it means that, let's suppose you set v mu just by definition equal to the derivative of dx mu over dt, evaluated at t equal to 0. This is independent of f, okay, so it's fine. But also d over dx mu is independent of f. So finally, you can see that, yeah, you have used that to define your vector, but actually, in the end, you can define the vector just by as a differential operator. So the differential operator v mu times d over dx mu, evaluated at the point P, is the tangent vector in P along the direction of gamma. And now this object here are a sect dx1, let's say, over dt, dx m over dt. So these are certainly a set which belong to Rm, evaluated at t equal to 0. And they form a vector space. And given any, can I move?
Not yet. So okay, thanks.
Excuse me, what is the F exactly? I mean, the map between what manifolds?
F is a map between M and R. Just any map, have a differentiable map between M and R. It's used, it's not something that is used to be able to define something which is independent of the chart. Because when you define the derivative in the previous slide, we define that way. This is totally independent of the chart, it's totally independent of coordinates. And now the trick is that, okay, this is fine, but now we use intermediate step the coordinates. And now we try to extract from this something which do not depend on F. And it turned out that what do not depend on F is just V mu times d over dx mu, which of course is written in terms of coordinate, but since our original definition did not depend on the coordinate, it's independent of the coordinate itself. And so it's not related to one particular map. So the original problem in the naive definition is that it depend on the chart, but this does not depend anymore. Now I can comment on this because these objects form a vector space, clearly. And given any vector let's have be a vector in Rn, of course there exists a curve gamma through P such that dx mu over dt evaluated at t equal to 0 is exactly equal to v mu. Well, just take a curve which in coordinate is just x mu coordinate of p plus t v mu. And obviously this has the correct property. So this is really a vector space associated to P and independent on the chart. This is called the tangent space at P. And it is denoted by TPM. So this is the vector space. Dx mu over dt at t equal to 0 d over dx mu. This is our the mate of this vector is a tangent space at P of M, and it is noted by. What is a basis? Well, the basis is obvious. The basis of the space is just a set d over dx mu, from mu equal to 1 to M, because we have constructed our vector just by combining some coefficient with this basis. And now let's see if I change the basis. So it means that I change basically my coordinates. If I change the basis, let's consider a new basis, the new coordinate x prime m. Well, this is equal, of course, to d over dx prime m, dx nu, d over dx nu. But V, originally our V was independent, was chart independent. Is chart independent. Because we have defined through the definition, remember that we have defined it through the definition d over dt f composed gamma of t, which don't know anything about the chart. So it means that b mu d over dx mu must be equal to v prime mu, the new object, new component, d of x prime mu. But now, because d over dx prime mu, this is equal to v prime mu, d over d x prime mu x nu times d over dx nu. And so, v prime mu is equal to dx nu divided by dx prime nu to the minus 1 times v nu. Which is precisely, this is a standard definition of a contravariant vector. So not only we have found that this is it is a vector space, it is independent of the chart, but also the component of these vectors satisfy exactly the standard definition of contravariant vectors. So we have achieved our result. This is really the correct definition of a vector in a manifold, which we have been able to introduce through this differentiable structure that we have introduced in this clever way. So the only point is that compared with a standard usual argument in which you think the vector has a kind of a little arrow, now the vector is really a differential operator. You cannot think it in terms of a segment-oriented segment. No, now it's a differential operator. This is the price that you have to pay to define it intrinsically. Okay, and now of course you want to know how you map vectors from manifold. So suppose you have a map between vectors in manifolds. So you already have your original manifold, maybe M. You have some curve gamma, you have a defined. Naively, you would say, well, if this would be just a little arrow, you just map this vector here to initial point and final point to some initial point and final point in another manifold, N. So you have some f of gamma and you define it naively, but this doesn't work. But vectors are differential operator now. So how you define a map? The way we define the map is again through a trick, going through some function. And the map is called the push forward. Is the map given a map F? The push forward, which is denoted by a little star in the lower indices, lower index, is from the tangent manifold at P of M, space of M at P, to the tangent space of F of P, let's call it Q, let's say, of the manifold N. And again, you use the trick. You take a smooth function C, let's say, for example, C infinity of N, and you define the following, to which you apply our differential operator, which represents our vector. And how you do it? Well, you say that our vector was, you can write as f star of b. So given a vector b, which belongs to Tp of M, you define a vector b star of v, which now acts on a function g, which is a function in N, just by V acting on G composed F. So this is the correct thing because NG was a map from N to R. G composed F is a map from M to R. So you can apply V as a differential operator to this object here as we have done before. So if you do it, so basically the idea is that, okay, you have a map F from M to N. Now you use a function G from N to R, same trick. Now, of course, you can do in coordinates. Locally on M, you can construct a chart, phi of P, which goes into Rm, and you denote the corresponding coordinate by X. So you can also construct a map phi of Q, which is equal to F of P in Rn, and you denote the coordinate by Y. And now if you do this, the push forward of the vector V mu over D over dx mu acting on G must be equal to V mu D over dx mu acting on G composed F. And again, same trick as before. You introduce some intermediate step. You use G composed phi Q to the -1. Now we use phi Q composed F, composed phi P to the -1. And now again, this is from R, you take it from Q to the -1, so Rm, F, Rn. So this is from Rm to Rn. And now you bring it from Rn to R. So everything very well defined. And so now you can see it in terms, can I move?
1 second, please.
Yeah, just one moment, please. Thank you.
Can I move?
Okay, ready over here. What about over there?
Okay, so now let's do in component. Push forward of V component nu D over dy nu acting on G must be equal to V mu D over dx mu acting on G of Y of X. So according to this is equal to V mu D over dy mu of G of Y D over dx mu of Y nu of X, which implies that F push forward of V component nu of push forward of V is just V mu dy nu over dx mu, which looks like a change of basis, but is not a change of basis, because F might not be invertible. So this is a worry, kind of worry. This looks like I changed the basis from X to Y, but this is not true. It has the same structure, but this is not the same thing. Now that I have defined my space Tp of M, the natural question is, what is the dual space of Tp of M? Well, let's denote, it will be denoted by Tpm star. Okay, so what is, by definition, should be the definition of dual space given by maps, by linear maps, which map a vector from a vector V, which belongs to TP of M, to R. And furthermore, we want that its component transform like dx mu divided by dx prime mu. And we want the basis in the notation that I note in my note for the tensor calculus. So if E mu is the basis of our vector space V, the basis of the dual space V star is such that they must satisfy this. And what is that satisfy all these properties? Well, just given a real function, real C infinity if you want function, define df is a map which sends you V to Vf. V, remember that V was a differential operator. So when you act it on a function V, so this object here is really something which is linear in V, and it maps into some point in R. And the basis also is very simple. The basis, just take at F, special case of F, you can take dx mu. So dx mu applied to the basis, which was dx mu. Well, this is nothing but dx mu, the partial derivative with respect to dx mu. But this we know that it is d delta Kronecker of m of mu nu. And so, but df, you can also now write in this basis is df over dx mu, partial derivative with respect to mu, times dx mu. And so, fine, you have found your basis. Your basis is just this differential, and the action is the one I wrote here. And now you're doing components. Let's see if it has a correct property of transformation. Can I move it?
From my side, yes. I don't know about the others.
Yes, too.
And now what is our in terms of components? For df, you have df of dx mu, and now change the coordinate. Df over dx prime mu is equal to df over dx mu times dx mu divided by dx prime mu. So, okay, is exactly what we wanted. And so everything works, and this is the dual space of TP of M. And now using we can extend the tensor calculus in this way, which we have discussed, all in any domain of the charge. For example, if you have Rm, you need only one charge. So certainly in Rm, you can extend. So now finally, we come to the P forms. So a P differential form, and many times this differential is not written explicitly. What it is just a completely antisymmetric tensor field of type 0P. So components are covariant. In the notes, it's written clearly now, they form a vector space. I mean, these are P form in a chart, in the domain of the chart. We will discuss the general case in which you are not in the domain of a chart. I mean, in the general, you need some more mathematics. So I hope to be able to discuss it in the band when we discuss the bounds. So they form a vector space.
Mm.
And
May I ask a question?
yes,
Where
please.
does the anti-symmetry now come from? Why do we demand this?
So the anti-symmetric is a requirement that you have. By definition, a P form has X component completely anti-symmetric, which means that if you exchange two indices, you must get a minus sign. Is it
We
clear?
haven't motivated it at this point, have we?
Why it is so? Okay, in order to see why it is important, we have to reach the point where we make an integration. The point is that this property is corresponding to introduce a kind of Jacobian in the change of coordinates, which automatically satisfy the property that you need for integration. Okay, but I now don't know how to justify this yet. This is one thing, and the other is that when you can differentiate one of these forms, because of antisymmetry, you have some special properties that cancel the double derivative on the same coordinate transformation because of the antisymmetry. And there are, okay, maybe there are many reasons why this is very important. Okay, so let's see if we can go. So this is they form a vector space. The basis we know it is just, we have already discussed in the first part of the note, dx mu1, let's say dx mu p. Wedge product between these so that a P form in a chart is given by 1 over P factorial. This is just a question of normalization. Some completely antisymmetric, totally antisymmetric tensor dx mu1 wedge dx mu p. And let's see, like one of the virtues of this. You can easily define a derivative of this, which is called the exterior derivative. What is the exterior derivative? Is some map P, which maps to a P form into a P plus 1 form. Okay. When I write some antisymmetry, what is the way in which it acts? Okay, maybe you're already familiar with, okay, maybe, sorry. Is it fine to move it? Can I move?
I need a moment. Thanks.
Okay. So, yeah, I think you are familiar with the symbol of antisymmetrization, but I just recall if you have some object, mu1, mu p, and I note the note with this symbol, I just mean that, so let's say mu(n), to be completely general. Is thus definition 1 over n factorial, which is the number of permutations of n indices. The sum over all sigma, which are the permutation in sigma n, this is permutation of n objects. We come back to this. -1 times pi of sigma is the number of exchanges in this permutation of t pi of mu1 pi of mu(n). So you make the sum of all possible permutation, you multiply by -1 to the number of exchange in that permutation. This is totally antisymmetrization. Well, dA of P by definition is 1 over P factorial. You take the derivative with respect to the component x mu of a mu1, a mu p, And now you anti-symmetrize all the indices, and then you multiply by dx mu1, dx mu, wedge dx mu1, wedge dx mu p. Okay, so this is by definition a exterior derivative of a P4. And now it comes the real one of the key property of the P form. Let's do it twice d. D of dAP is what? Is 1 over P factorial, derivative with respect to mu, derivative with respect to x nu, A mu1 mu P, dx mu, wedge dx mu, wedge dx mu1, dx mu P, totally anti-symmetrized. Well, but this is totally anti-symmetrized, but d mu is equal to d mu, so it's symmetric. So if anti-symmetrized is 0. So you immediately get that, or alternatively, you can say that dx mu, okay. This is also antisymmetric. Okay, this is antisymmetric. So when you contract, this is antisymmetric. Okay, so now we have that dd as an operator is equal to 0. And so now we can use a terminology. Let's consider a P4, AP, is said to be closed if dAP is equal to 0. And is exact if there exists a P-1 form such that AP is equal to D of AP-1. And now it is clear that since DD is equal to 0, every exact form is closed. However, but not the very important thing is that not all closed forms are exact. So there is a possibility that you apply the derivative on some domain S, on some subset of S, a subset of M. There is one case in which you are sure that if you have a closed form is also exact, and this is when you have this subset of Rm in which you have defined your form is what is called a contractible set. Let me give me an idea of this is 2, however. For a contractible set, so S contractible. What means it is contractible? Let me give first an idea what means contractible. Can I move?
1 second, please.
Yes, one moment, please.
Pieralberto, you have still a bit more than 10 minutes.
Okay, when I finish, I finish.
Perfect.
Okay, so what is contractible? Okay, it means that for every point Q which belongs to S, there exists a continuous map. So contractible set, S contractible. If for every Q belonging to S, there exists a continuous map, let's call H of Q, which goes from 0, 1 cross S to S, which centers so from 0, 1 I call T, the point in S I call P, this is sent to some point which I call h of t of p, such that h of 0 and p is equal to p, and h of 1 p is equal to q. If I do in drawing, suppose you have a set like this. Our set is S, is this object here. I pick a point Q, and it's almost clear that I can map all these points here because I can make continuous map by changing, and I can take a point, for example, a point here, a point here, a point here, a point here. I can certainly do it for every point I can map into Q. But if I have a set which is given by an object like this, so our set is this, and I pick a point Q, there is no way in which you can make it continuously because you can try, but at you can map this into this, you can map following this into this, but at some point here you cannot do it anymore continuously. Okay, then, so this is a contractible set. This is non-contractible set. And so, I mean, the key idea is what is called the Poincaré lemma. A differential form in a contractible set if it is closed. There is also exact. This is a crucial point. If you have a contractible set, fine, closed and exact coincide. Let me give a counter example, which is similar to this. Let's consider R2 minus the origin. And define the form, which is, maybe you know very well, dx dy minus y dx divided by x squared plus y squared. So it is well defined because x squared plus y squared is different from 0. Now if you go in polar coordinates, of course, what this is just, you just choose x equal to rho cosine theta, y equal rho sine theta. You perform everything, and what you find is that it will be rho square cosine square theta d theta plus rho square sine square theta d theta divided by rho square, so it's d theta. The point is that this is not exact. Why? Because you write the theta, but actually there is no function of this property which is continuous, because this is 0, 0. Now you consider theta, and now when you approach this line, theta is equal to 0, but on this side, theta is equal to 2 pi, so this is not a continuous function. So even if you write formally in this way, this is not an exact form in R2 minus 0, 0, in spite of the fact that it is a well-defined form in R2 minus 0, 0, okay? So this is a closed form, which is not exact.
I have a question. Does the notion of non-contractible or contractible set coincide with simply connected?
No, it is more than simply connected. It is more than simply connected. For example, a two sphere, okay, is simply connected.
Yes.
But it's not contractible. You cannot map the point of the sphere to one point. You can, I mean, the logic is similar to this one. So you are
on
not
this, on the surface of the sphere, I can contract.
On the surface, sorry. I mean, what I call sphere is just the surface, okay, of a ball.
Yes. And
You pick a point you can try to move each point, but at some point there will be the opposite. Let's say you want to map everything to the North Pole, but you never succeeded it continuously in the South Pole.
okay.
Okay, now now the same thing. How a map F from M to N induce a map on
Professor,
P4.
your writing is off the screen.
Okay.
Thank you.
How a map F from M to M induces a map on P4. Well, again, same trick. Suppose you have now I call an R form because I need the P to the P. Unfortunately, I should P also for P form, and P is the point on the manifold. Okay, anyway, I call an R form, and you have F. So now what you do is, we know that we can map again by locally phi F phi of P. You have a point in Rm, which, and here you have phi Q, which is we have a point in Rn. And now, no chart. We want to do it without chart. Well, define the following object: F star of A of R. Now this is, we define acting on V1 up to VR, which each one of these belongs to TP of N.
Let's see if it works with this.
Can you hear me?
Yes.
Yes.
Yeah.
Okay, you define as the form AR acting on the push forward of V1, push forward of VR. And now, since this was a form, remember this is now a form on M. So in this way, we are in opposite of what happened before. Given a form on N through this map, which is F with a star, which is an upper index, you go to form on M. If F is a map from M to N, so F map M to N, here you have your T star N, here you have T star M, and you given a form here, okay, you define what is a form here. So AR was, okay, so let me dust the main components. This is called the pullback. Okay, so let me do it in components. So this was a TP of M. This is push forward. We know that it is will be belong to TP to F of P of N. And in component, F star of the R form of this is a form, as I said, a form on M. So it is dependent on coordinate X is 1 over R factorial A nu 1 nu R of Y of X. So now it depends on X. dy nu 1 of X wedge dy nu R of X, which you can also write 1 over R factorial A nu 1 nu R of Y of X dy nu 1 over dx mu 1 dy nu R over dx mu R times dx mu 1 wedge dx mu R. So you see, this is really a form on M, which is this very strange coefficient. And now a particular pullback is induced by the embedding of the P surface. Sorry, I did. I move it.
Yeah, just a moment, please.
Pieralberto, you have in theory 2 minutes left.
Okay, I think I finish with not glue the current.
Thank you.
Okay, so a particular pullback is induced by the embedding of a p-dimensional manifold, let's say sigma of p, in Rm. M, of course, greater than p. For example, you have your torus and you embed it into R3. This is a sigma 2 and you embed into R3. So let's call I the map in which we embed sigma p inside Rm. Then you can define what is called the pullback of a p form. So AP was a p form defined in Rm. I star of p, the pullback through I, is a p form on this surface, sigma of p. And now this permits to define the integral of a p form on sigma p. Because you define the integral on sigma p of this p form, by definition, is the integral on sigma p of the pullback of this form, which is now a form on sigma p, that you can write explicitly using, if you have your coordinate is a sigma 1, sigma 2, for example, on this torus, you write as a mu1, mu p, as a x, which is a function of sigma 1, sigma p, according to the rule that we have said, dx mu1, d sigma mu1, dx mu p, d sigma partial sigma mu p, times dx mu1 wedge dx mu p. Notice this is independent of charge. And this, because of the anti-symmetry, this behaves like a Jacobian. And that's the reason why this is independent on charge. If you change coordinates, it doesn't matter, because this behaves exactly like a Jacobian. So you are able to define the integral of a p form on a p-dimensional surface.
Am
So
I
now you
correct
have
that
seen that.
I think it must read d sigma nu 1 wedge to d sigma nu p.
Sorry, yes, sigma u1, sigma nu p. Sorry, yes, sorry, right. Sigma u1, sigma nu p, right, thank you. Sigma u1, sigma nu p, yes. And so this is a form on sigma upon sigma of p. Now you see the power of the forms. We have seen that the p forms have the property that you can easily define the derivative through the exterior derivative. If you try to do it for a general tensor, there will be second derivative on the tensor if you do it naively on the coordinate transformation. You can act twice of the same. But now it is forbidden, because if you act twice with two coordinates, because anti-symmetry, they skip 0. So one property is this. Another interesting property is that there is some difference between close and exact, and then this suggests, and in fact it is true, that through the closeness but not exact form, you can get some information on the topology of your space. And finally, because of the transformation, which is defined through the embedding, through the pullback, you have exactly the property of the Jacobian. It automatically defines in a consistent way the integration of a submanifold of your system, of your RDRM. Okay, I don't know what I have additional time. Probably not.
No, it will be for next time if that's okay.
Huh?
Okay, so thank you, Pieralberto. So the next pre-lecture will be on Monday at 2 p.m. CT with the last lecture of Christian. And then later in the week, we will have then Pieralberto continue what he has started today. Okay, so I will now turn off the recording so that everyone that wants to ask a question can do that.